Suppose that C is a smooth curve described by the position vector function r, where the x component is a function of the parameter t, the y component is a function of a parameter t, and the z component is another function of the parameter t, where t is in the interval from a to b. Then the arc length function s is defined by s of t is equal to the integral from a to t of the square root of the sum of the squares of the derivatives of our components of our position vector function. In other words, the arc length function is the function defined by the integral from a to t of a velocity function with respect to u du. So what this theorem allows us to do is to generate a function based off of a parameterization of a curve. Similar to how we calculated the length between 2 points, this is going to be the length between a point and an arbitrary location on the curve. Let's say we have an arbitrary function in space. This function is given by the equation r of t, with an x component being a parameterized function of t, the y component being a parameterized function of t, and the z component being a parameterized function of t. On some interval ranging from t equals a to t equals b, we want to know a function that governs the arc length. So in other words, for any value of t between a and b, we want to know what our function is at that point. So this curve here, we'll call this curve the arc length s as a function of the parameter t. So if we change t, that'll just give us a different length for the curve. If we go to another value of t, being a function of t, we'll have another value for the arc length. So that's what the arc length theorem tells us, is it gives us an expression for the arc length as a function of the parameter as long as our position vector function is differentiable in the interval, in the closed interval from a to b. Let's explore this with an example. Find the arc length function s of t for the curve defined by the position vector function with an x component of 1 plus t, a y component of 1 plus 2t, and a z component of 3t for the interval ranging from 0 to infinity, so all positive values of t. And then we're going to use our result to find a parameterization of the curve in terms of the arc length. Let's begin by writing down our position vector function r, having components of 1 plus t for the x component, 1 plus 2t for the y component, and 3t for the z component. Now, if we look at these components one by one, see if you could recognize what type of curve this is. So what do you think? Well, notice this curve describes a parametric set of equations for a line. Our position vector function r describes a line. And remember, For a parametric set of equations for a line, in standard form, we define it with a point on the line and a vector parallel to the line. So a point on the line is given by these first coordinates, these first values here. So we will call our point on the line x naught, y naught, and z naught is the point 1, 1, 0, which if you notice, since the z coordinate is equal to 0, this is a point in the xy plane. And also for our equations of a line, that's described by a vector parallel to a line. That vector parallel to the line has components given by the coefficients of the x, y, and z coordinates, respectively. So this is the vector parallel to our line. This is how I recognize that this position vector function actually represents a straight line in three-dimensional space. Let's just sketch it, see what the sketch tells us. So I will create our sketch on an XYZ coordinate system where the z-axis is vertical, the y-axis is horizontal, and the x-axis is coming out of the page straight towards us. Let's do some scaling on the x, y, and z axes. I'll just do some units along the x-axis, our scale along the y-axis, and a scale along the z-axis. Now to plot this point, I'm going to pick that point on the line. So the point in the xy plane with coordinates 1 for the x coordinate, 1 for the y coordinate, and 0 for the z coordinate. So that puts us right about here in the xy plane. Now to graph this, and this is going to be a little bit challenging because we're trying to construct a three-dimensional graph on a two-dimensional screen or paper. But how I'm going to graph this is I'm going to begin with that point, and let's go ahead and label this point the point 1, 1, 0. Let's begin with this point, and let's do the trace of this in the xy plane. So in the xy plane, I see I have a vector. So I'm looking at the velocity vector, or rather, not the velocity vector, the v vector. Again, that's the vector parallel to the line. So in the xy plane, I'm going to look at the xy component of that vector that's parallel to the line. I see the x component is 1 unit along the x-axis. So let's go up 1 unit along the x-axis. That would be this right here. So that's 1 unit from our starting point of x equals 1. And then we are going to go 2 units along the y-axis. Well, 2 units from our starting location of y equals 1 puts us at y equals 3. So in the xy plane, our line has that shadow if we were to project down from the z-axis. Now the z-coordinate of our vector parallel to the line is 3. So that means we have to go 3 units up. Let's take a look at that. I'll just do 3 units on my z-axis. And then let's translate that over to our point in the xy plane. And this is how high we have to go. So now what I'm going to do is I am going to just connect our point 1, 1, 0 in the xy plane, have it pass through the top of that line and continue on. This right here represents the sketch of our curve, and this sketch, again, is given by 1 plus t for the x component, 1 plus 2t for the y component, 3t for the z component. And notice this sketch starts at t equals 0, because if you notice the z component is equal to 3t. So when t equals 0, we are in the xy plane. So this sketch does represent the parameters or the constraint given to us in the problem, which said come up with a position function for positive values of t. Now that we have sketched our position vector, let's go ahead and calculate its arc length function. So the arc length as a function of t is equal to the integral from a to t. Well, in this case, a is going to be 0 because we're starting off with the parameter values of t that are positive, but including 0. And then this is equal to the magnitude of our velocity vector as a function of u du. Now remember, velocity is just equal to the derivative of the position vector with respect to our parameter. Here it is u. So this is the derivative with respect to u of 1 plus u, 1 plus 2u, and 3u, where I've replaced t by u so we could put that into our integral. When we evaluate the derivative of this position vector with respect to u to get velocity, for the x component we get 1, for the y component we get 2, and for the z component we get 3. That's what we called v before. And now we get the same thing. And that makes sense because the velocity of a curve at any point tells you the direction of that curve. And when we determined that we had a parametric set of equations for a line of our curve, and we knew that the v vector was a vector parallel to the line, well, it makes sense that the velocity vector would yield the same thing because, as we've shown in a previous lecture, velocity is always tangent to a curve at the point at which you evaluate it. Now that we have our velocity function, let's calculate its magnitude. The magnitude of the velocity is equal to the square root of the sum of the squares of the components of the velocity. This is equal to the square root of 14. So now we have the arc length function is the integral from 0 to t of the square root of 14 du. Well, when we evaluate this, well, the square root of 14 is a constant. When we evaluate the integral of u, or the integral of du, that is u, evaluate it from 0 to t. This then is just the square root of 14 t minus 0. Or we end up with the arc length function being equal to the square root of 14 t. We now know the length of this line for any positive value of t. And notice from this result, the arc length is a linear function of t. Now that makes all kinds of sense because We earlier said that this represents an equation of a line. The equations we were given, the parametric set of equations, represented the equation of a line. And being an equation of the line, it makes sense that the length of the line between any 2 points on the line beginning from the xy plane would change linearly. For example, if we double the value of t, the length of our line, or the length of that segment of line for which we're calculating the arc length, also doubles. So this is a good confirmation. The sketch helps confirm our result. So the last part of this problem says, use your result to find a parameterization of C in terms of the arc length S. So in other words, they want us to find R, the position vector function, as a function of S, which S is a function of t. So that's the goal. Find R as a function of S. Currently, we have R as a function of t because that position vector as a function of t is given as 1 plus t for the x component, 1 plus 2t for the y component, 3t for the z component. So if we want to express R as a function of the parameter S, let's go ahead and then express t as a function of S. And we could do that from here. Here, just rearranging this, we get t is equal to S over the square root of 14. So this means that R as a function of the arc length is equal to 1 plus S over root 14 for the x component, 1 plus 2 over root 14 S for the y component, and 3 over root 14 S for the z component. So why might that be useful to do? Well, let's say we want to know what point in space we're at when we've covered 30 meters along our curve. Well, 30 meters is a length. We could just plug in the length into this position function and we would know where on the curve that is. Or what if, it's saying, okay, where are we at when we are at a length of 2 meters or 2 units? Well, we would plug in 2 meters into this position vector function, and that'll tell us where we are. So the difference between the two, between the position vector function we are given and position as a function of arc length, is the position vector function we were given is in terms of a parameter. So you might think of that parameter t being time. So that might tell us where we are in time. But expressing the position vector function as a function of arc length tells us where you are after covering a distance. So one can be thought of as where you are in time, and the other one can be thought of as where you are in distance. That's one possible reason of why we would want to express a position function as a function of arc length.